Welcome back to JVM Internals Crashcasts. I'm your host Sheila, and today we're diving deep into the Java memory model. We're currently in level 3 of our series, exploring expert-level topics in JVM internal architecture. This episode is part of our chapter on concurrency and synchronization, and we've already covered thread management and synchronization primitives. Joining me as always is our JVM expert, Victor. Hello, Victor.
Hello, Sheila. It's great to be here. The Java memory model is a fascinating topic that's crucial for understanding how Java handles concurrency at a low level. I'm excited to explore it with you and our listeners today.
Before we dive in, let's start with a quiz question for our listeners. Here it is. True or false? The Java memory model guarantees that all threads will always see the most up-to-date value of a shared variable regardless of how it's accessed or modified. Think about it, and we'll reveal the answer at the end of the episode.
That's an excellent question, Sheila. It touches on some common misconceptions about the Java memory model. I'm curious to see how many of our listeners can get this right. It's a tricky one that really tests your understanding of JMM's guarantees.
Indeed. Now let's start with the basics. Victor, could you explain what the Java memory model is and why it's important?
Certainly. The Java memory model, often abbreviated as JMM, is a specification that defines how Java threads interact through memory. It's crucial because it provides rules for how changes made by one thread become visible to other threads. Without the JMM, we couldn't write reliable multi-threaded programs in Java.
That makes sense. So, it's like a rulebook for how threads communicate, right? Can you give us an analogy to help visualize this concept?
Absolutely. Think of the JMM as a postal system for a large organization. Each thread is like a department in this organization. When one department, thread, wants to send a message, update a variable to another, they don't directly hand it over. Instead, they put it in the mail system, memory, and there are rules about how and when these messages are delivered. Sometimes messages might not arrive in the exact order they were sent, or they might take some time to be delivered. The JMM defines these rules of delivery.
That's a helpful analogy, thanks. Now, you mentioned that messages might not arrive in order. Can you elaborate on that? It sounds like it could cause problems.
You're right, Sheila. This is where we get into the concept of memory consistency errors. In multi-core processors, operations can be reordered for performance reasons. This means that without proper synchronization, one thread might see the effects of another thread's actions in a different order than they were actually performed. This can lead to what we call counterintuitive behaviors in concurrent programs.
That sounds tricky to deal with. How does the JMM help us manage these potential issues?
Great question. This is where the happens before relationship comes in. It's a key concept in the JMM that defines a partial ordering of program actions. If one action happens before another, it means the effects of the first action are guaranteed to be visible to the second action. The JMM provides several rules that establish happens before relationships, such as the synchronization actions on the same monitor, writes to volatile variables, and actions in a thread before spawning another thread.
Interesting. You mentioned volatile variables. Can you explain what those are and how they relate to the JMM?
Certainly. The volatile keyword in Java is closely tied to the JMM. When a variable is declared volatile, it tells the JVM that this variable might be accessed by multiple threads. The JMM then provides two key guarantees for volatile variables. First, it ensures that any write to a volatile variable establishes a happens before relationship with subsequent reads of that same variable. Second, it prevents certain types of reordering involving volatile variables.
That's really helpful, Victor. It sounds like Volatile can be a powerful tool for concurrent programming. Are there any common misconceptions or pitfalls related to Volatile that our listeners should be aware of?
Absolutely, Sheila. One common misconception is that Volatile solves all concurrency issues. While it ensures visibility of changes, it doesn't provide atomicity for compound actions. For example, operations like increment, I++, are not atomic even if the variable is volatile. By atomicity, we mean that the operation is performed as a single indivisible unit. Another pitfall is overuse of volatile. which can hurt performance due to the memory barriers it introduces.
Speaking of memory barriers, can you explain what those are and how they relate to the JMM?
Of course, memory barriers, also known as memory fences, are low-level operations that control the ordering of memory operations. The JMM uses these barriers to enforce its rules. There are different types of barriers: load-load, store-store, load-store, and store-load. Each type prevents different kinds of reordering. For instance, a store-load barrier ensures that all stores before the barrier are visible to other processors before any loads after the barrier.
Wow, that's getting into some low-level details. How does all of this impact everyday Java programming? Are there best practices developers should follow?
Great question. While most Java developers don't need to work directly with memory barriers, understanding the JMM is crucial for writing correct concurrent code. Some best practices include: 1. Prefer using higher-level concurrency utilities like Java util.concurrent classes instead of low-level synchronization. 2. When using low-level constructs, always consider visibility and happens before relationships. 3. Use Volatile judiciously for simple flags or counters where atomicity isn't required. 4. Be aware that even seemingly simple operations can have unexpected behaviors in a concurrent context. 5. When in doubt, use proper synchronization mechanisms.
Those are really helpful tips, Victor. Now, as we're nearing the end of our episode, could you share how the Java memory model compares to memory models in other languages?
Certainly. The Java memory model is generally considered more straightforward than some others, like the C++ memory model. Java's model is designed to strike a balance between allowing compiler and hardware optimizations and providing strong guarantees for programmers. In contrast, C++ allows for more fine-grained control but can be more complex to use correctly. Some languages, like JavaScript, have only recently defined formal memory models, while others, like Python, rely on implementation-specific behaviors due to the global interpreter lock.
That's fascinating, Victor. It really highlights the importance of the JMM in Java's design. Now, let's wrap up by revealing the answer to our quiz question. The statement was, the Java memory model guarantees that all threads will always see the most up-to-date value of a shared variable, regardless of how it's accessed or modified. Victor, is this true or false?
The answer is false. The Java memory model does not guarantee that all threads will always see the most up-to-date value of a shared variable. It only provides these guarantees under specific circumstances, such as when proper synchronization is used or when the variable is declared volatile. Without these mechanisms, threads may see stale values due to caching or reordering of operations.
Thank you, Victor. To summarize today's episode, 1. The Java memory model, or JMM, defines how threads interact through memory. 2. It provides rules for visibility and ordering of memory operations. 3. The happens before relationship is key to understanding the JMM's guarantees. 4. Volatile variables and memory barriers are important low-level constructs in the JMM. 5. Understanding the JMM is crucial for writing correct concurrent Java programs. In our next episode, we'll be moving on to our chapter on performance tuning, where we'll discuss JVM flags and tuning options. Don't forget to subscribe to JVM Internals Crashcasts and leave us a rating if you're enjoying the series. Thank you for listening, or